Hello everyone, my name is Ajahn Pumidet and today I'm going to review you the electrochemistry knowledge from your freshman or your general chemistry class or even some high school. That's why I call this video Freshman Electrochemistry Revisited. So first, let's talk about what is electrochemistry. So you can see that electrochemistry is constructed from two words, right? Electricity and chemistry. So, electrochemistry is actually a discipline of chemistry that studies the relationship between electricity and chemistry, or we can call it the relationship between chemical chains and electricity. For example, if we apply some electrical current or electrical potential, how will our chemical component in the system change? Or vice versa, if we change some chemical component of the system, how does it change the electrical properties of that system? In electrochemistry, we usually have some chemical reaction, and we call those reactions redox reaction. So, redox reaction involves an electron transfer between the reactants. For example, if you have seen the Symmetry Experiment in which you put the copper wire in the solution of silver nitrate and you leave it for a while, and as a result, you get the tree composed of the silver metal, and your solution gonna turn blue because of you gain more copper 2 ion which has blue color. So from this Symmetry Experiment, we can write the reaction as follows. So copper solid plus 2 silver ion in aqueous. And you get 2 silver metal as the product and the copper 2 ion. And notice that we put 2 here in order to balance the charge because at the reactant side you have 2 plus ion. You have 2 plus charge. So at your product you must have 2 plus charge as well. So this is the reaction of the Symmetry reaction. So here you can see that starting from copper solid, you get the copper 2 ion, which means that copper solid gives the electron to the silver ion. Or, in other words, silver ion receives or gains the electron from the copper solid. So again, here we can see that copper ion from reactant, at the end, you get copper 2 plus ion, which means that copper gives the electron to something else, which in this case is the silver ion, and it converts itself to copper 2 ion. In contrast, silver ion receives or gains the electron from copper. So it changes to the silver metal, which has zero charge. So again, you can see that redox reaction, you must have one species giving the electron and one species receiving the electrons. But here you can see that this is the redox reaction, and there may be some reaction which is not redox reaction. For example, I'm gonna write it here: silver nitrate in aqueous plus sodium chloride, right? And I think you have tried this before. You're gonna get the precipitation of silver chloride as the product, and sodium nitrate is still dissolved in the solution. So in this case, this is just like the ion rearrangement. So there's no like electron transferring between the species, between the reactants. So this is not the redox reaction. So with that, we can just delete this because we are not interested in this reaction. So now we have the redox reaction. Actually, I think you have learned this before. So redox is constructed from two words: reduction and oxidation. So reduction half reaction is the reaction of the species that gains the electrons. So in this case, it is silver ion. So we start with silver ion. And we get silver neutral as the product. So the charge change from 1 plus to 0, which means that the silver ion receives 1 electron. So we're gonna write it here. So this indicates that the silver ion gains the electron. So that's why this is the reduction half reaction. So in contrast, the oxidation half reaction is the reaction with gives the electron or lose the electron. So in this case, it is the copper, right? Copper 0 loses 2 electrons. So we can write as copper solid give you copper 2 ion, and it also gives you 2 electrons, which can transfer to the silver ion. So we already talked about reduction and oxidation. What if we want to talk about the species only? So I'm gonna write here as well. So here we can say that because silver ion oxidizes copper, so we call silver ion oxidant or oxidizing agent. In contrast, the copper solid goes to reduce the silver ion, so we call the copper solid reducing agent. So notice that this is a little bit confusing, so you may have to slow down a little bit. So the oxidizing agent oxidizes something else, but itself is being reduced. So in this case, silver ion goes to oxidize the copper to copper 2 plus, but the silver ion itself receives the electron. So this is why the silver ion, being the oxidizing agent, but it is reduced and undergoes the reduction. In contrast, the reducing agent undergoes oxidation. So in this case, copper solid reduces silver ion to 0, but the copper itself has to lose the electron. So the copper, which is the reducing agent, is being oxidized or undergoes oxidation reaction. So we have finished the redox reaction. There are actually many ways, or at least 2 ways to have the redox reaction occurs. One way is to mix the reactants together. That is, for example, in this case, you may have the beaker. You have the solution of the silver nitrate, which are actually silver ion. And then you put the copper wire. So if you zoom in a little bit, there's going to be the direct electron transfer. We call it, again, direct electron transfer. Direct electron transfer between the silver ion and copper. That is, you may have the copper ion here, and then you have solid copper. And then copper can give 2 electrons to the silver ion, but you need 2 silver ions here. So this is the direct electron transfer between the species. Another way of having the redox reaction occurs is through the electrochemical cells. So this is more useful way to have the redox reaction because we can utilize the energy from the electron transfer, for example, in batteries or fuel cell or something else. So you can utilize that energy to give us the electricity, for example, in our cell phone. So in this case, what will happen here is that we can construct 2 half cells. And I'm gonna write here. We can construct at least 2 half cells. So in this case, instead of mixing the copper and silver ion solution directly, we can just construct 2 half cells. The first half cell is gonna be the beaker, and then a solution, and then you put the metal. So this is copper, and this is copper 2 plus, such as copper sulfate, maybe. Actually, it can be any inert salt is fine. The second half cell is going to be silver, of course. So this is the metal, and then that's the solution, and this is silver, and this is silver ion, like maybe silver nitrate, I don't know, depends. So you have to half cell. Now you're gonna need to connect them together to have the electricity or the electron flows. So you need to connect it with the electrical wires. So this is the electrical wire. But this circuit is actually not complete yet because it may turn out that electron can flow in only one way, and when the short time passes, you don't have the reaction anymore because the charge is imbalanced. So in this case, you're gonna have to add. I'm gonna draw the blue thing here. You're gonna add something called salt bridge. Add something called salt bridge, which is actually a tube with saturated electrolyte like potassium nitrate or sodium sulfate, and you may have some porous fluid, so to prevent the contamination or leaking. And you may even use the filter paper, like the saturated filter paper with this kind of salt to connect between these two half cells. So what's gonna happen is that once there's the electron flows, right? In this case, we know that the electrons from copper half cell gonna flow to the silver half cell. So we may write as this. So electron here goes to here. So you're gonna have more negative charge at the silver half cell. So we need more positive charge as the silver half cell. It turns out that, for example, if we have potassium nitrate here, the potassium ion gonna migrate to this half cell, this silver half cell, and nitrate ion gonna transport to this copper half cell in order to preserve the balance of the electrical charge. So again, we already know that we connect two half cells together. In this case, we have copper half cell and silver half cell, and you need the electrical wire and you need the salt bridge to preserve the charge balance. And then you get your electrochemical cells. You didn't really put any external energy into it. This is the spontaneous reaction, right? This is the spontaneous reaction. And the redox reaction occurs in the electrochemical cells with spontaneous reaction is called galvanic cell. Galvanic cell. Or sometimes you will see the word voltaic cell. That's the same thing. So this is the galvanic cell. So the reaction in these electrochemical cells is going to be the same as the one that we already discussed in the silver tree, which is copper solid plus 2 silver ion, and you get the silver metal and copper 2 ion as the product. So this is the same reaction, but it's just occurs through the electrochemical cells. Sometimes you want to construct the electrochemical cells to have the redox reaction which has no solid phase, like the redox reactions of a lot of ions. So in that case, you may use the inert electrode. For example, maybe platinum or carbon is going to be your good inert electrode. For example, I can construct this cell. So this is going to be a beaker with iodide solution and mixed with iodine molecule, and you put the inert electrode, which is in this case is platinum. And then another half cell is, so this is a solution again. And then here you have a mixture of permanganate ion, manganese 2, and proton. And you put another inert electrode, which is platinum. What I mean inert electrode is that it cannot undergo any reaction too easy. It just acts as the electrical conductor, that's it. And then once you have two half cell, again you can just put the electrical wire and then the salt bridge. I'm just gonna draw something like this as a salt bridge. So this is your half cell of the inert electrode. So we already draw at least two electrochemical cells, but sometimes it's very hard to draw and you want to communicate easier than this with other people. So we use something called cell shorthand notation. Let me draw it. Let me write here cell shorthand notation. And this is like in any standard chemistry textbook, like should already say something about it. So this is like the shorthand notation to describe this galvanic cell, only galvanic cell. For example, for this copper and silver half cells, we can write it as copper solid, and you use one vertical line to separate between the phase, and copper 2 aqueous. Usually you will tell the concentration as well, but if it's in the standard state, which is like 1 molar solution or 1 atmosphere of gas, then you can just ignore it. So I'm just gonna ignore it here as well. So this is copper. And then if you have a salt bridge or you separate it with the junction, you will put the double vertical lines. And then you write the rest, which is like here, silver, aqueous, and silver. So we already finished talking about electrochemical cells in general and the cell shorthand notation. So let me actually copy this cell and put it here. So in this topic, we're going to call it galvanic cell and electrode potential. So we already have like this half cell that have the reaction occurs. But what if we put the voltmeter between it, which means that we have to delete this and then connect this again. But now you put voltmeter. I'm going to use the electrical circuit symbol here. So in general, voltmeter will have a high resistance or high impedance so that the reaction will not occur yet, but at least you get some, and then you get some voltage or electromotive force to read. The number that you can read from voltmeter is called cell potential. Cell potential. Or we can use the symbol E cell. And of course, since we have only two electrical components here, which is the copper half cell and the silver half cell, so your cell potential is going to be the difference between the potential of this half cell. We call it electrode potential. And we have two electrodes, so I'm just going to put S here, electrode potential. Now, the problem is that how you're going to define these two electrodes. So again, we already said that in redox reaction, there's going to be one species undergo oxidation and another species undergoes reduction. So similarly here, we will call the half cell which undergoes oxidation as anode. I'm going to write here anode. And the another half cell is going to be cathode, which undergoes reduction. So obviously in this case, here, your copper half cell undergoes oxidation. So this is the anode. And your silver half cell undergoes reduction. So this is cathode. So your electrode potentials, you're going to have some symbol called E anode and E cathode. So, and we already said that the cell potential is the difference between the anode and cathode cell potentials, the anode and cathode potentials. So we get this this family equation: E cell is equal to E cathode minus E anode. So this is very important, and you have to remember this. So E cell is equal to E cathode minus E anode. But sometimes we want to talk about like the cell with the negative potential, which means that the reverse reaction occurs. We're gonna use something like right and left. So we can also say that E cell is equal to E right minus E left. This is like the same thing, right minus left. And if we go back to the cell shorthand notation, this is left and this is right. And we already see here that the copper, which is on the left, is the anode. And this is the cathode, the silver one. So the cell shorthand notation, I forgot to tell you. So to write the cell shorthand notation, we usually put the anode first and followed by the cathode later. So that's why we can use the word left and right also to indicate the half cell in your cell. But now the question is that is there anything that like affects the cell potential and electrode potentials? The answer is a lot. Maybe temperature, maybe concentration, or the gas pressure, or even some contaminants. To give you more convenience to discuss about the electrochemical cells, we're gonna have to specify the standard condition, which is like 1 molar concentration. Strictly, we're gonna call it like activity equal to 1 molar concentration and 1 atm or 1 atmosphere of the gas, and then pure solid or pure liquid, depends. And the potentials of the cell and electrode under these standard conditions is called standard cell potential. Let me write here. Standard cell potential and standard electrode potential. And you can put the not symbol. So here it's gonna be E naught cell equal to E naught cathode minus E naught anode, something like this. So this is in the standard condition. So we already talked about the cell and electrode potentials, but what do these numbers mean? So the physical meaning of this number is the difference in the ability that each half cell want to give electrons or want to receive the electron. In other words, the standard electrode potential tells you whether that half cell or that electrode wants to be reduced or oxidized to what extent. And these numbers, the values of the standard electrode potentials, are specified in the table. So you can just go to your chemistry textbook and find your table, right? And then you can calculate the cell and the electrode potential, of course. For example, let me go back to this silver and copper electrochemical cell. If we know that the number of this voltmeter is 0.46 volt, and we know that the copper 2 plus has the electrode potential of 0.34 volt. What is the electrode potential of this silver half cell? So we can use E cell equal to E cathode, E anode. I'm gonna just put this abbreviation here. And we already know that E cell is 0.46. You can put the not or not, depends. 0.46. And your cathode, which one is your cathode? Is the silver, right? And you don't know that yet. So I'm just gonna put it like this, and minus 0.34, right? From the anode. And then you use your calculator, and you know that the potential of this cathode is 0.80 volt. For example, this is like the basic calculation. This is how you use the number to predict the cell and electrode potential in the electrochemical cells. But these standard electrode potentials are more useful than that. Actually, you can use these numbers to predict whether the redox reaction can occur or not. For example, let me go to the new place here. If we want to know whether the nickel metal can be oxidized by oxygen or not in basic condition, we can use the standard electrode potential, the relevant standard electrode potential to predict the reaction. And the reaction is given here, which is like 2 nickel plus oxygen plus water, and you get nickel ion as the product plus 4 hydroxide ion. So how to do this? First, you separate the reaction into the reduction and oxidation. So the reaction on the cathode is oxygen. Cathode is oxygen plus water. Actually, there's 2 here. Oxygen plus water plus 4 electrons, and you get the 4 hydroxide ion. And then the anode is going to be, of course, your nickel. So this is nickel ion, and 4 electron because you multiply by 2. Now you go to your standard electrode potentials table, and then find the potential. So it turns out that the cathode has the standard potential of 0.40 volt, and anode is minus 25 volt. So the E cell is going to be like E cathode minus E anode, which is what? 0.40 minus 0.25, which is plus 0.65 volt, which is more than 0, which means that this reaction is spontaneous. In other words, nickel metal can be oxidized by oxygen in basic condition. So again, I'm going to write the summary here that if the standard cell potential is more than 0, then the reaction is spontaneous. And you may know that like the equilibrium constant is going to be more than 1. But if your E cell is less than 0, then this is going to be non-spontaneous. And your chemical equilibrium constant is going to be very low, lower than 1. The last point to make here before we move to the next topic is that we always use the standard cell and electrode potential, which is defined in the reduction direction. Standard electrode potential is defined in reduction. You cannot flip the sign and call it oxidation potential. This is very important. So this is also wrong as well. You cannot do this. All right. We always talk about it as the potential, which is defined to the reduction reaction. So previously we talked about the cell and electrode potential at the standard condition. But what if it is not in the standard condition? We can use the equation to calculate the new electrode and cell potential. And this equation is called Nernst equation. Which is very important, and I actually expect you to remember this equation. So the Nernst equation is E cell equal to standard cell potential minus RT over NF and natural log of the reaction quotient. R is the gas constant, right? 8.314 joule per mole Kelvin. T is the temperature. N is the number of electrons transferring. And F is the Faraday constant, which is 96485 coulomb per mole electron. And here is the reaction quotient. But we may be more familiar with the form at 25 degrees Celsius, which is fair enough. So at 25 degrees Celsius, we can use E cell is equal to standard cell potential minus 0.0592 over N log base 10 here. For example, for the silver and copper reaction, we can write the reaction again here. So this is copper solid plus 2 silver ion, and you get the silver metal plus copper ion as the product. And we already separate the reaction, right? So you get the N is 2. So the Nernst equation of this at 25 degrees Celsius is going to be cell potential equal to standard cell potential minus 0.0592 over 2. Because if we go back here, where is it? If we go back here, then this is 2 electron. And you have to balance this as well to get that the number of electron is the same. So this is 2. Multiplied by the base 10 logarithm of the Q. Now Q is the basically like the same form of the chemical equilibrium constant. So this is gonna be silver metal, which we won't include it here. So this is gonna be only copper 2 over silver. But since silver has 2, so we have to put 2 in the exponent. So this is the Nernst equation of this reaction. What about the nickel and oxygen reaction? We can write the reaction again. The Nernst equation is going to be cell potential equal to standard cell potential minus 0.0592 over N, which is what we can go back to here. So you can see 4 is the number of electron transfer. So you put 4 here, and then log base 10 of nickel to the 2 and hydroxide to the 4 over nickel. We don't include oxygen, but oxygen is the gas, so we may want to put something like the pressure of the gas, of the oxygen gas. And water, of course, we don't include. So this is the Nernst equation of this reaction. And one way to use the Nernst equation is to use it to predict the behavior of something we call concentration cell. So concentration cell is constructed from the identical electrode and half cell, but the concentration is just different. For example, we can construct the concentration cell of the copper. So this is copper. This is also copper, and then you connect it with maybe a voltmeter, and you put the Saw bridge and whatsoever. But this is the copper 2. This is also the copper 2 ion, but the concentration is different. For example, this may be 1 molar. This may be 1.0 molar. And this may be 0.1 molar. From the Nernst equation, you may see that because the concentration of copper 2 ion is different, so the cell potential is not 0. And you can write it as like cathode. Cathode is copper 2 with 1 molar, because you can guess that at the end the concentration of the copper in 2 half cells should be the same. So this is going to be decreased, and this is going to be increased. So to decrease the copper 2, this have to undergo the reduction, and this has to undergo the oxidation. So this is cathode, and this is anode. So this is why we write 1 molar side as in the cathode. So this is copper 2 and 1 molar, and then plus 2 electron, and then you get copper. And the anode is just going to be the opposite one, which is copper solid. and you get copper ion, 0.1 molar plus 2 electron. So the E cell. So the next equation for this specific concentration cell is gonna be this one, right? And then E cell, it is the same half cell, so the standard electrode potential is gonna be the same. So this term is 0. So this is the next equation, and you substitute the concentration, and you will get something like 0.3 or volt as the cell potential of this concentration cell. So this is the application of the Nernst equation. And so in our analytical chemistry class, we can see that the concentration of the electroactive species or the analyte will affect the cell or an electrode potential. And also vice versa. We can also control the cell and electrode potential to indicate the concentration of the analyte in our analytical technique. So we have already talked about one type of electrochemical cell, which is galvanic cell. For example, we can go back to this like the silver tree like cell, which is like the copper is oxidized and the silver ion is reduced. But what if we want to flip the reaction? Which means that what if we want to reduce copper to plus 2 copper and oxidize the silver? So this is kind of in the opposite way of the spontaneous reaction, right? Opposite to the nature. So we have to apply the external energy, maybe by battery or some energy source to it. And in this kind of cell that we put the external energy to drive the non-spontaneous reaction, we call this type of cell electrolytic cell. And the reaction here, the redox reaction here is called electrolysis. So just to make it more simple, we can draw it again, right? So and then usually the electron flow in this direction. And then we already know that the cell voltage is 0.46 volt. If we want to flip the reaction, it means that we have to put, so instead of the voltmeter, I'm just gonna put something else, which is the battery. And I will use green. Let's say I will use green to put the battery. And then, but the external voltage, this is going to be the external voltage. And the magnitude of the external voltage must be higher than the standard cell potential from the galvanic cell, which means that this one have to be higher than 0.46 volt, in order to flip the reaction to the electrolysis that we want, right? So in this electrolytic cell, we're gonna have the copper ion being reduced to copper solid, and your silver metal gonna be oxidized to get more silver ion, which is in opposite to the nature. So this is the reaction of the electrolytic cell, which is in the opposite side or opposite way of the galvanic cell. But so now what we are more interested in here is the amount or the magnitude of current to drive the electrolysis. And you may be not familiar with the words, but I think you have calculated this before in your Gen Chem. The relationship between the amount of product and the current, or actually charge and time, is controlled by something called Faraday's law of electrolysis. Faraday's law of electrolysis. Which says that the amount of the electrolysis product is proportional to the charge that flows through the cell. Again, the amount, I'm just gonna use this here. The amount of electrolysis product is proportional to the charge that flow to the cell. That is, if we know the amount of the charge, then we can calculate the amount of the product. And you may be like, do we need the equation for this? Actually, you don't really need the equation. Like, all you have to do is to use the factor label method. Or maybe one equation that you want is this equation from your physics, which is like charge is equal to current multiplied by time. And here we assume that your current is constant. If your current is not constant, you may have to like integrate something like this. But let's not talk about it here. So let's do some example here. So this is like basically the cell without liquid junction. So you have this electrode. This is gold. Let's say this is gold electrode, and this is let's say you want to electroplate some of your object. I don't know, maybe your key, maybe some fancy thing, and then you apply the external voltage to it, to this one, and this is in the solution of gold 3+, maybe gold chloride, and this is going to be your anode, and this is going to be your cathode. Now let's calculate the amount of the gold that you're going to get if we apply 0.5 ampere current for 1 hour. First, what you need to know is the electrolytic reaction. So from gold 3+ to gold metal, you need 3 electrons, right? So this is actually gold 3+ plus 3 electrons, and you get gold as the solid. Now you want to use the factor label method or the stoichiometry. So let's start. So let's do it. Q equal IT, right? So this is actually 0.5 ampere multiplied by 1 hour, but we want to convert hour to second, which is the SI unit. And 1 hour is like 60 minutes, right? And 1 minute is 60 seconds. So this is actually 3600 seconds. 3600 seconds. And this is going to be Coulomb already. Ampere second is Coulomb, of course. Now you can use the Faraday's constant, which is 96485 Coulomb per mole electron. So you get mole electron here. But you want to convert it to mole of the gold. So from the electrolytic reaction here, to get 1 mole of gold, you need 3 moles of electrons. And multiplied by the molar mass of the gold, which is from the periodic table, which is 1967 gram gold per mole electron or per mole gold. And that's it. You will get the mass of the gold, which is about 1.22 gram of gold. So this is how you use Faraday's law of electrolysis. And in our analytical chemistry class, we will learn that we can quantify the amount of analyte, maybe the concentration or the overall mole or mass of the analyte, by just counting the charge or measuring the current, and we will learn how the current and charge is actually related to each other in our electrochemical techniques. So that's it for the electrochemistry revision. So to review, so we already talked the definition of redox reaction, that it has the reduction and oxidation, and how to call it like oxidizing agent and reducing agent. And there are 2 ways to have the redox reaction occur. Maybe the direct electron transfer, and maybe undergoes the electrochemical cells. In electrochemical cells, we talk about the galvanic cell first, and we label and we define anode and cathode, which we use copper and silver half cells as the example here. And the galvanic cell is the cell of the spontaneous reaction, and we learn how to describe it to use the cell shorthand notation. And we talk about the inert electrode as well in case of the redox reaction without the solid electroactive species. and we define a little bit about the cell and electrode potential and the relationship between the cell potential and the cathode and anode potentials and the standard condition as well, and the meaning of it, and to use this equation to calculate these kind of potentials. And then we learned that we can use the electrode and cell potential to predict the spontaneity of the redox reaction, like the nickel and the oxygen in this basic condition. And we talk about the Nernst equation if we want to predict the cell and electrode potential out of the standard condition. And we use it to describe the concentration cell as well. And lastly, we define and we talk about the electrolytic cell, which we have to apply the external energy in order to drive the non-spontaneous reaction. And we quantify the amount of the electrolysis product from the charge, which is the current multiplied by time, according to this Faraday's law of electrolysis. So that's it for the clip. Thank you so much and see you in the class. ขอบคุณครับ